How many of you watched Jensen's keynote from a couple of hours ago? Thankfully, very few of you, because this presentation would be extremely boring after that. However, the rest of you, please make sure you watch it as quickly as you can, because there's some amazing news, amazing progress in technology and ecosystem that Jensen shared. So, we've been talking about robotics, edge computing for a long time. Why? Very simple, right? Quite simply, the largest opportunity in the history of humanity. Much of the world is physical. 80-90% of the world's GDP is in the physical world. In fact, automation has been existing for over 60 years. But we still haven't cracked the code for bringing autonomous capability into physical AI and robotics. And you can test it in many different ways. You can ask, how many robots, industrial robots, cobots, AMRs, with any sort of autonomous capability, how many are shipping right now annually? You could pick a number, 1 million, 2, whatever. But then you ask yourself, what is really the opportunity that is in front of us? It's billions, if not tens of billions, right? So we are at least 1,000, if not 10,000 times away from making this happen. So the vision has always been there. Personally, for me, the vision's been there since I was born because I was watching Star Wars and Star Trek. Pretty much everything that's supposed to happen is kind of depicted in those movies. So what makes it so tough? Why hasn't it happened yet? And are we about to change the trajectory? Do we have enough things to actually make it happen? I think there's many reasons, but there's 2 reasons fundamentally why autonomous AI in robotics and physical AI hasn't happened, and that we need to solve. Without that, we can't go. Number 1, of course, is accuracy, right? You all probably are using ChatGPT or Claude or Gemini or DeepSeek or whatever it is for your personal use, for recommendation, for summarizing email, for writing email, any of those. The accuracy has, of course, gotten better and better in the last 3 years. But in almost all cases, there's a human in the loop, in this case ourselves, we finish the email. But when it comes to the real world in physical AI, there's not going to be a human in the loop. So the accuracy requirement is extremely high. You can typically measure it in how many nines after 99 point, right? Depending on if it's a self-driving car, it's probably 6 to 8 nines. If it's a surgical robot, you probably want it to be 15 nines. Maybe if it's an AMR, maybe 2 or 3 nines is okay, it depends. But in all cases, the accuracy is so high that until you hit that mark, you can't really make it useful. We still haven't cracked that accuracy code. And you can test it. How many robots are really autonomously shipping in the world today? So that's number 1 problem we have to solve. And number 2, once the robots become reasonably intelligent and accurate enough for specific tasks, you need to make sure that these robots integrate into existing workflows in the real world. For example, if you try to deploy these robots in a factory, manufacturing factory, there are many existing workflows already deployed, right? From, what humans do versus what each of the assembly lines do, traditional computer vision, optical inspection. There is, factory operating systems. There's many different, protocols, PLCs that all exist in the last 30, 40 years. This robot brain or robot brains that are going to come in, they need to play nice and integrate with all of these different systems. And that integration is extremely difficult to write programs for because some of these are like 20, 30 years technologies. So until we solve those 2 things, number 1, accuracy of these AIs. Number 2, easily integrate these AIs into the existing workflows. Physical AI robotics will not take off. Okay, so with that, I'm going to tailor my presentation towards exactly what NVIDIA is doing in helping the whole ecosystem in the industry solve these 2 problems. So for robotics, You guys hear all this cracking, or is it just me? I'm going to move off that a little bit. It's pretty noisy there. So what are we doing to solve the accuracy problem? Remember we said that the accuracy requirements are extremely high, 99.9999 and so on and so forth. It turns out robotics need 3 computers. Most of the time when we talk about a robot or physical AI, usually our mind always jumps to the destination, which is the robot itself. We're talking about edge computing, we're talking about deployment. But remember, we can't deploy until it's accurate enough. Otherwise, you can't really scale. So the final destination, of course, is the deployment. That's the edge computer. That's the 3rd computer. But before you deploy, you got to test it and make sure it is absolutely safe and accurate enough to be deployed. And testing, the best place to test robots, physical AI, happens to be in simulation because it's faster, safer, and cheaper. Until recently, the sim to real gap, what you simulate versus what happens in the real world, was not close enough. So you couldn't really believe what you simulate, which means it's pretty much useless. Many of you here have been working in the chip industry. Every chip that any one of us tape out is 100% simulated, emulated before we send to the fabrication, right? The fab. So in that case, we know that whatever we simulate, emulate before we tape out absolutely works. So we need that same capability to come to robotics. And of course, robotics is incredibly harder because of the real world physics and a lot of things, the lack of data. So we need a second computer which is to simulate it. And of course, before you simulate it, you have to train the brain, and it's a lot of computes required. So you have to train these, what started with large language models, went into multimodality vision language models, action models, and now in the last few months, we're starting to see that's not sufficient, so you need to actually model the whole environment. You have the world models and world action models and so on and so forth. Incredible research progress happening in all of these. So what do we do at NVIDIA? We build the 3 computers. Training, number 1, testing and simulation, number 2, runtime deployment, number 3. And then we provide the reference workflows, acceleration libraries, reference models, all the reference software to help you in this whole journey. Number 1, to generate data. Number 2, to train the model. Number 3, to test the model, evaluate the policy in simulation. And number 4, lastly, you deploy the model. And remember, once you deploy a model and bring robots into the real world, that's not the end of the journey. In fact, I would argue that's the start of the journey, because these robots will be operating for 5, 10, 15, 20, 30 years in the future, right? And these robots will be continuously becoming more and more intelligent and more specialized for those tasks, which means this flywheel of data, train, test, deploy is a continuous life cycle journey. So that's basically what we do at NVIDIA. So the first problem we have is, how do you create an intelligent model that is accurate? Well, before ChatGPT, we all remember, right? It's like, it feels like it's like so long ago, but it's just been like 3.5 years since ChatGPT came about. But before ChatGPT, if you remember, AI existed, right? Since 2012, the AlexNet moment, to 2022, for 10 years, we had AIs deployed primarily in the form of convolution neural networks and transformers and so on. But the AIs were what we call specialist models that were doing one specific job, right? If you're trying to build a car, you'd have many different models, but each model, one model would be doing lane detection, one would be doing sign detection, one would be doing, path planning, and so on and so forth. So same thing was true for robotics. NVIDIA, we started working on solving these robotics problems back in 2013, and we've seen a vibrant ecosystem. There's over 10,000 companies in the world that work with us in many different industries, many different use cases, all trying to make the robots more and more autonomous. We've been making good progress, but we haven't really hit that accuracy mark. And the problem was, of course, when you create a specialist model, it kind of works for that scenario, but the world is mostly unstructured, semi-structured, things keep changing, it's never static. As a result, the models are brittle and they don't work in all the different conditions, and that's why robotics hasn't taken off. So the way to solve that problem is very similar to what ChatGPT did. ChatGPT was that moment that said, instead of building a specific model for weather, one model for finance, one model for reading, one model for so on, for the first time ever, there was a reasonably good enough generalist model that was built, right? ChatGPT was that first time a reasonably general purpose model that was trained on the whole, everything, pretty much everything we put on the internet, all sorts of text, right? Books, speeches, and so on and so forth. For the first time, a general purpose model came out. And since then, you see how fast we're off to the races. Everybody starts with that starting point, and then you derive specialists from that generalist. Another way to think about it is, like, you can actually hire forget child labor, but you can actually ask your kid to do a task. Let's imagine your kid is 10 years old. They can do some tasks, but you don't hire them into your company. Why? You wait, they're at least typically 21, 22 years old, have an undergraduate degree, because that's when we believe that's a reasonably good enough generalist. And then from then on, once they come into your company, they are going to become more and more specialized for the next 30, 40, 50 years, right? So until you hit that generalist moment, it's very hard to solve these problems. So right now, the whole robotics industry, from the latest, greatest startups to the best researchers in the world to large companies, we are on a quest to build a ChatGPT type of reasonably good enough general purpose model that is accurate enough for certain robotics tasks. We are not there yet. Okay, so what is the number one problem to create that, for us to create that ChatGPT model? Well, in the case of ChatGPT, you can guess what was the number one problem. Compute was the number one problem. But once we had enough compute, that was solved. But in the case of robotics, it's not about training the model. Actually, where do you even get the data to train the model? You can't take YouTube videos and make a good enough industrial robot. You'll probably have a good dancing robot, but it's not going to be really solving precise tasks for the accuracy that you need, right? So how do you solve this problem? Well, you can go and collect lots of real-world data. That's happening right now. There is, people are collecting from teleoperation to imitation learning to seeing general-purpose videos, right? All of those are good things, necessary, but absolutely not sufficient. And it turns out the answer is, again, using AI to take those, whatever real-world data is available, to create many scenarios. And that's where we spend a lot of time right now. Data is the number one problem today until we get the right kind of data. And it turns out it has become, compute is data. So you need a lot of compute. So we have several technologies. Everything is open source, from NVIDIA Cosmos, which is a World Foundation model. And Jensen, by the way, shared a lot of information about Cosmos today. Cosmos 3 was announced. It can basically create many, many different scenarios, leveraging 3D accurate models to create, predict what the motion is going to look like, what the action is going to look like, create the whole surrounding. So Cosmos is one technology. You can also use real-world sensors on your cars or your robots to actually capture the real world and then generate a full synthetic environment, something called NVIDIA NeuRec technology. So we spend a lot of time on that. We spend a lot of time, accelerating for teleoperation, collecting real-world data. So that's one of the biggest contributions that's happening now, enabling you to collect lots of data in order to train a reasonably good enough model. Once you have the data, you're going to create a model. That's pre-training. But once you create that model, you're going to deploy it into a specific embodiment that's probably going to specialize in certain tasks. You don't need every robot to do everything possible. You don't need a robot to be the best tennis player, best golf player, best plumber. You don't need that. I mean, that's too expensive and unnecessary. So what will happen is you'll create a good enough general purpose brain, just like us humans, and then each robot brain will become very specialized in a certain task. So that's the number one thing that we do, is help all the roboticists to create great data in order to improve the accuracy of the model. Now let's imagine for a second we've collected real-world data, now we've created all the synthetic data, and we have sufficient data to train the model. And let's imagine we had infinite compute to train the model, to generate the data, and we have a model now. How do you have to test it, right? And if you try to test it in the real world, operating on wall clock time with the number of robots that we have, it will take decades, if not centuries, to solve some of these problems. We have to speed it up, orders of magnitude. And it turns out simulation is the answer. And the problem until recently was the sim to real gap wasn't good enough. We haven't completely solved it, but for many use cases, it's gotten close enough that we can actually address this, especially for rigid body manipulation. For locomotion navigation, simulation is now good enough to solve the sim to real gap. For rigid body manipulation, it's quite close. And for soft bodies and fine-grained dexterous manipulation, with new physics engines that we're working on in open source, that's also coming together. So we spend a lot of time in our simulation environment for data generation, environment generation, for policy learning, reinforcement learning-based policies. And then once the model is created, trained, you have to test it in simulation. So we spend a lot of time doing that. So notice I didn't spend a lot of time talking about the third computer, which is ultimately the destination. And the reason I didn't spend a lot of time on that computer today is we can't get there until we solve the robot brain and testing the robot brain. And we're working with literally, the whole ecosystem of partners across the world in many different capacities. You got companies that are building robot brains. We got companies that are building full robots. You got companies that are building special purpose hardware. Advantech, of course, is one of our great partners, cutting across, commercial robots to industrial robots to all sorts of use cases, specialized computer to provide that robot brain. We're working with literally every company to create simulation environments, right? And then, of course, you need access to lots of compute. So, and then sensors and actuation and being able to model the sensors and actuation in simulation is essential. Because how do you test the model in simulation if your sensor is not accurate in simulation? How do you test your actuation in simulation if your actuator is not captured in simulation? So this whole new field where physical companies have to also have a digital twin or a digital cousin, whatever you want to say it, equivalent of it in simulation. So we're spending a lot of time on that. And of course, once you have that, then we all know how to solve the IoT problem. We know how to solve the edge computer problem. We know how to solve the runtime problem because we all have been working on PC industry and the phone industry and the car industry, and we know how to deploy all of these edge devices, but we need to solve that accuracy problem. All right, so now let's say we solve the accuracy problem. You got a great robot. It's like this. Let's say you have a job opening in your company. You hired a great engineer. Great. Intelligent engineer, you brought him into the company. But if that engineer doesn't work well with the rest of you, it's completely useless, right? It's counterproductive. That engineer needs to integrate into your company, follow the process, work with everybody else. The same thing is going to be true for factory operations, city operations, manufacturing operations, logistics operations. And it turns out just like a factory has many different workers, many capabilities, the same thing is going to be true with these autonomous robots, right? You will have robots of different capabilities in the future. You'll have humans in there, different embodiments of these robots. You'll have digital AIs. All of them need to be orchestrated and working together. Who's going to orchestrate all of those? Who's going to write the code to integrate all of those? Impossible for a human to do it. Thanks to Agentic AI in the last few months, this is the answer. So when we solve the accuracy problem, thankfully we have agents to make it easy to orchestrate all of these sub-agents together. So with that, Miller, can I call you back on stage to talk about what we can do together to experiment? How can we implement this sort of a system into your Advantech, of course, manufactures a lot of things. How are you thinking about it?
All right. Yeah, Deepu, thank you. You clearly explained very clear strategy from NVIDIA for physical AI lending to our industry, from robotics, from also leverage the Agentic AI, NeMo Cloud, Agentic AI tool. So yeah, here's the new strategy from NVIDIA for factory operation blueprint, Fox strategy and program. So aligned with Advantech, we also like to propose our idea. Because of Advantech, we also have quite a big space of the manufacturing campus. Talk about our Lincoln campus. This is our Lincoln campus. Contribute more than 40% of our production capacity, right? So by leveraging align with NVIDIA strategy, we'd like to install the factory brain idea concept into our factory to upgrade our manufacturing operation. So our product team, product group, ESG product group, Magic and the team, they are working with our factory team together to come out 5 initiatives. Okay, you can see from the production, quality, operation enhancement, and also the autonomous robotics, and also energy management. Those 5 initiatives will be developed into our Lincoln campus as a pilot run. So I think it is will very support Advantech to transform our manufacturing operation. And also will be a great demo site to show the NVIDIA and Advantech AI factory brain solution.
Yeah, that's great, Miller. So as you can see, there's many different use cases and applications there, and each of those require autonomous AI, and each of the technology will advance at a different pace. For example, inspection is advancing fairly fast. We can see now with these latest vision language models that the accuracy of and reducing the false positives is taking shape very fast. But as each of these technologies mature differently. However, having a LLM, a factory brain, enables you to, irrespective of how mature each one is, you can add and delete new processes. So that's going to be a significant advantage.
Yeah, sure, absolutely sure. That leverage NVIDIA silicon platform for Jetson Solar, Jetson IGS, and also RTS Pro solution, we can not only building up full range of the Advantech hardware, edge computing, edge server product line. Also, we can practice it, realize it in our own factory. So once it's ready, we welcome you, and also our partner can visit our Lincoln campus again.
Are you promising a demo next time you're here?
Yeah, we'll promise, we'll commit. Our team are working very hard to make it happen. All right?
All right.
Thank you.
Great. Thank you.
Thank you, Deepu.